All right, pre-calculus. This is a video for section 10.6 on parametric equations. Here I am in Desmos, and I'm going to show you how to graph parametric equations in Desmos. What you do is you plot a point, except then you use the parameter t in the coordinates of your point. So let's say you want, normally if you plot a point like this, 2, 3, it plots a point at 2, 3. But if I put like t comma 3, then what it does is it makes it introduces this parameter t, and it gives us a range of values. I'm just gonna go -10 to 10. So what that did is it made a horizontal line, because what I'm saying is that just that the x coordinate is given by the value of this parameter, and the y coordinate is always equal to 3. So y coordinate is a constant. Now, what if I want it to be something else? Like what if I want to do like maybe t squared in there, right? Then t comma t squared gives me this parabola, like y equals x squared, because basically the y is the square of x. So y equals x squared is exactly what this is trying to graph, right? So that's the same thing. Yeah, so you can do all kinds of things here. You can, make t squared as well. If t squared, if they're both squared, then you get this straight line because they're basically equal to each other. So you get a +2 on there. It shifts over a little bit. Maybe we make this one cubed. Okay. You can get all kinds of different graphs from these things, and so you can just put whatever function you want inside here, like this, t minus 2, t squared. Maybe we can put like a sine of t in one of them. Maybe t times sine of t, and we can get something kind of wacky going on there. There's all sorts of different things we can do. So what I'm actually going to do is rewrite this as f of t comma g of t. Now that I've got to insert some lines above this, and I'm going to define what f is. F of t is going to be, let's call that t, and then g of t is going to be plus 5. There we go. Now I'm going to take f of g and f of t and g of t, and I'm going to make both of these. I'm going to hide them both. So these are the actual functions. I'm going to hide both of them. So now what I have is this function f of t g of t. So now this is the equation, or sorry, this is the graph of that set of parametric equations. That's x and that's y. This is kind of cool because now what I can do is I can write f of a comma g of a, and then get a slider for a and have this slider go from -10 to 10, and then I can hit play. And I can watch this thing bounce along. Actually, I'm going to change it so they both go, so it goes forwards, and it's just going to repeat. So there we go. So now you can kind of see the whole idea of t being time, and then f of t g of t gives you the coordinates of a point on the graph of the parametric equations. And then as time goes by, that point moves along, and so the graph essentially is tracing out the pathway of that point through time. So a great example of this is if we do the circle, the unit circle. Let's do cosine of t for our x function. Remember, f is the x function. And then let's do sine of t for our y function. And there you go. So now we have this going around. And actually, I'm going to adjust this now so that instead of -10 to 10, I'm going to go 0 to 2 pi. That is exactly one lap around the circle. By the way, if I do it from 0 to pi, you see you just get half the circle, which is, sorry, ignore this for the moment. You just get half the circle if you go from 0 to pi, right? If I go from 0 to pi over 2, I get a quarter of the circle, that kind of thing. You can pick whatever range of values you want, and that's a range of angles that you'll describe. Like if you go pi over 3, right? And there's from pi over 3 to 2 pi. So you can pick whatever range of angles you want, and that's the portion of the circle that this will show. I want the whole circle, and I'm going to do the same thing with my a here, 0 to, 2 pi. There we go. And now I can show this, and I can plot. And so now we can see this, see our point going around the circle. And as t increases, the moment in time, it's sort of corresponding to the angle, and it's looping around nice like that. Okay, so now that I've got the unit circle, now what I want to do is explain to you all how we can graph other conic sections. So first of all, let's say you want to shift this circle so that it's centered somewhere other than the origin. Doing that all we actually really need to do, pause this here, all we really need to do is actually just take our x and our y. So this is x and this is y, right? I've got to take x, and if I subtract 2, what should happen is it should shift 2 units to the right, right? If we subtract 2 from x. But what I can do is move that to the other side of the equation. It becomes plus 2. And so now defining my function f of t like this, where it's cosine of t plus 2, what this means is my x coordinates are going to be the cosine of t plus 2 more. And that will shift all of the x coordinates 2 units to the right. So shifting to the right and left and up and down is really easy. All I've got to do is take my parametric functions here, my individual functions for f and y, for x and y, and I've got to add or subtract whatever I want. If I want to shift it down by 3 units, I just subtract 3. So that's super easy. So what you want to do here is just add h and add k. Let's make sliders for h and k. And I'm going to put them at the bottom here. Or actually, here, I'll put them here. I'm going to add sliders for h and k, and now I can move it anywhere I want horizontally and anywhere I want vertically. In fact, on Desmos, you can do this. You can do h comma k, and then I can grab that and move it around. Oh, something's wrong. Oh, I know what's wrong. Oh, it's because I did minus. Plus. There we go. So now if k is negative, it goes down. If k is positive, it goes up. Right. So adding h and adding k at the end there and there makes it so that I can drag and move this wherever I want. Okay. So that's how you shift a circle. Add things. Now let's say I want to scale. All I got to do to scale, like say I want to stretch this out and make it a radius other than 1. All I've got to do is scale it by the radius I want in the x direction and the y direction. So let's bring this back to the origin here. Okay, plop. There we go. Stick it on the origin. Stick them both equal to 0. And let's make that equal to 0 as well. Okay, there we go. So now what I want to do, if I want to scale it, is I just want to multiply these by something. So say I multiply that by 2, that's going to stretch it out in the x direction by 2. If I multiply the sine of t by 2 as well, it stretches in the y direction by 2. So I'm just introducing a multiple to the cosine and the sine terms to stretch out by that factor. Remember that like multiplying on that side by 2 is just like dividing this side by 2, and you do this before the shifting. So forget about the plus h. Order of operations is you scale first, right? So if this was taking the x coordinate and dividing by 2, then that's going to scale it by a factor of 2 in the x direction. But moving that to the other side of the equation becomes just multiplying by 2, right? So there we go. So there is our shift. So now we can put a circle of any radius we want. We make this r and this also r. I can add a slider for r and have any radius I want, any positive radius. You can even multiply by a negative number, which gives you a radius, the same circle with the same radius. But you'll notice that when I make it negative, this point here, this red point, flips to the other side because r is becoming negative, but the graph is still the same. So there we go. And so that now introduces, that suggests that if I multiply by different numbers, as you saw earlier, you can make an ellipse. So this is what I was showing you earlier, is that you can make an ellipse. And so we can have this be any number we want, and this be any number we want. Let's say we make this like 5, right? Then what we've done is now if I center this, you can see clearly that the sort of half dimension in the x direction is 2, and the half dimension in the y direction is 5. Right there, it's 5. So so these are the a and the b values essentially. This is a is the half of the half the length of the major axis, and b is half the length of the minor axis. Okay, so so there you go. So this, if I now head over here, by the way, we can write down what we've learned. We can write down parametric equations for an ellipse. So if we're talking about x minus h squared over a squared plus y minus k squared over b squared equals 1, okay? If that's the equation we're working with, then the parametric equations will be like a circle, cosine of t, sine of t, except we're going to stretch by a factor of a in the x direction and by a factor of b in the y direction. And then we're going to add h on the x, so to shift it by h in the x direction. Then we're going to shift it by k in the y direction. And that is it. By the way, to confirm this, try taking these x and y, taking these functions here for x and y, and stick them in there and there. Stick them in place of x and y, replace x and y, and then what you'll find is that this all boils down to 1 equals 1, because the Pythagorean theorem, everything will cancel out, and the Pythagorean theorem will give you cosine squared plus sine squared on the left side. So that's pretty darn cool. These all this connect together, right? So now we can describe any ellipse. Now, what would you do if you wanted to describe, instead of an ellipse, a hyperbola? Right. So let's write down what it looks like for a hyperbola. Okay. We want parametric equations for a hyperbola. Well, first of all, the equation of a hyperbola is like x minus h squared over a squared minus y minus k squared over b squared equals 1. All I got to do is change that plus to a minus. Now, this is a hyperbola that goes this direction. This is a hyperbola that sort of opens. It has a horizontal transverse axis because the x term is first. Okay, so we could swap these around if we wanted it to go, the other way like that. Okay, so how are we going to do this? Well, this whole thing here, let's go back to this one for a second. This is all based on the idea that cosine squared of t plus sine squared t equals 1. So what we want something squared minus something squared equals 1. And there are different trig functions that satisfy a similar identity, but with subtraction. And the way you can figure it out is to remember that there's alternate versions of the Pythagorean identity involving secant and tangent, as well as cosecant and cotangent. So what you can do to make this work is you can use, let me erase these lines here. Oops. These. What we could do here is use secant and tangent, and the identity we want is secant squared t minus tangent squared t equals 1. So these are like equivalent to each other. This is an alternate version of the Pythagorean identity, but as you can see, this version has a minus in it. So what we can do is we can use x equals, we want x squared, we want x first, we want y second, right? So what we can do is have x be the secant, which is the first one, and y is going to be the tangent. It's the second one. Okay, so now we want to scale it in the x direction by a, scale it in the y direction by b, and we're going to add h, and we're going to add k, and that'll do it. Okay, so the only difference here is instead of using cosine and sine, we're using secant and tangent. So let's head back over to Desmos and graph that and see what happens. Okay, so back in Desmos now, remember my parametric equation is f of t, g of t, right? X is f of t and y is g of t. So what I've got to go do up here is change my x function so that this is going to be secant. Ooh, that looks interesting. Change my y function so that this is tangent. There you go. There you go. So currently this is scaled, 2 by 5. So let's adjust that back to just 1 by 1. And there you go. There is my nice little 1 by 1. Let's center it at the origin. Grab that and move that to the origin. There we go. It's pretty close. That's my little 1 by 1. You can imagine a little 1 by 1 square with the asymptotes running diagonally through the corners of the square. There's my hyperbola. That is exactly, if we did this right, that should be exactly x squared minus y squared equals 1. And there it is, right? X squared minus y squared equals 1. That's it. That's where a and b are both equal to 1, and h and k are both equal to 0. So obviously adjust h and k, and then adjust some a's and b's. You can do this, or you can do like that, make it a half, kind of do whatever you want with the scaling. So yeah, so there we go. And by the way, if you wanted to make it vertical, all you've got to do is change the order of these things. So use tangent and then secant. So if you swap the order, then it becomes vertical instead of horizontal. And let's just for fun, let's watch what happens as we play this. So A is still ranging from 0 to 2 pi, but because secant and tangent are still periodic, with 0 to 2 pi is a sufficient period to repeat it. Like 0 to 2 pi, it captures the entire secant curve and the entire tangent curve. So what we're seeing here is we're seeing the entire curve described with a domain of p value ranging just from 0 to 2 pi, and you can kind of see how the point moves along, over time, and how it traces out that curve. Pretty darn cool. Like it flies off to infinity and then comes back, right? It's almost as if the curve on the bottom right here is connected to the curve on the top left. And vice versa. The top right and bottom left are sort of connected, right? It's like it's going back around the back of the Earth, and then it comes back to the other side, right? Pretty cool. All right. So there's only one more type of conic section to talk about, and that would be parabolas. So the way to do a parabola is kind of simpler than hyperbolas and parabola and ellipses. We don't need to use any trigonometry for parabolas. If you have like a vertical parabola like this is just going to be basically y equals x squared, except then you're going to transform it, right? So y equals x squared, and then you can subtract h, shift it, and add k to shift it, and throw some sort of a scaling factor on there, and you can make any vertical parabola. Okay. So for that, what we can do is the trick I mentioned in a previous video, which is just to let x equal t, right? And then we're just going to have x equals t and y equals a times minus h squared plus k. That'll do it. So let's go over and display that one on Desmos. So f of t is my x coordinate. That's just going to be t. And then g of t, we're going to do a, and we'll make a slider for a in a second. That's the scaling factor. And then times x minus h squared, and then plus k. Where'd it go? Oh, it's because there's no a. That's right, I forgot. Let's do like a 2. Oh, something's wrong. Oh, I know what's wrong. I used x. I'm going to use t. That's what I meant to do. There we go. And so that's with 2. Oh, and the other problem here is that we're going 0 to 2 pi. 0 to 2 pi doesn't make any sense anymore. Let's go negative 10 to 10 again. Negative 10 to 10, which makes more sense now that we're not using trigonometry, right? We're not using trig functions, so we just want, basically we should use the domain like negative infinity to infinity, but I'm just going to do a segment of it, right? So here's a portion of that domain. Now HK, by the way, the HK point right here is now our vertex, right? Here's the vertex. And then the scaling factor is 2 currently. I could make it 1. That's a nice parabola. I could make it negative 1 if I wanted to open downwards. But scaling factor can be whatever you want. If you make it a, then, oh, it can't be a. It should be, let's call it like b or something. Yeah, you can scale that by whatever you want to get a nice skinny parabola or wide parabola pointing to up or down or whatever. So there we go. So the simple like x equals t and then y equals a parabola function will do it. Now you might be wondering what happens if I want it to be horizontal. Easy peasy. Just cut that, paste it into the x function, and then put the t in the y function, and now you have your horizontal parabola, and you can put that kind of wherever you want. The h and the k are backwards now. Like my h and my k don't match at all. I think you need to switch this so that this is k and this is h. There we go. There we go. Because we changed it from x to y, so that the h and the k have to swap as well. But there you go. So now that's how you do a horizontal one. So there you go. So now you know how to make how to graph any conic section, parabolas, hyperbolas, ellipses, and circles with parametric equations. So I hope you've enjoyed. It's a bit of a long video. But I think this pretty much does it for this lesson. So we'll see you next week.